Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in chapter 29. The figure shows the cross-section of a coaxial cable. At the center, a current I equals 1 amperes flows out of the page within a very thin wire. Within the cylindrical shell, a non-uniform current flowing into the page is specified through the current density J equals C over R cubed, with C equals 2.39 times 10 to negative 3 ampere meters. The inner and outer radii of the shell are A equals 3 millimeters and B equals 5 millimeters. A. Find the enclosed current everywhere as a function of R. For R is less than A, that is inside the inner shell, the enclosed current is I, which is out of the screen. For R is greater than A and less than B, I enclosed is the sum of the currents I, which is out of the screen, the current in the portion of the outer shell, integral G times dA, which is into the screen. Conventionally, we take the direction out of the screen as positive and into the screen as negative. Therefore, the enclosed current is I minus integral G times dA. Direction is out of the page. G is C over R cubed. dA is 2 pi R dr. R cubed is simplified by R. The constants 2 pi and C can be taken outside the integral sign. So the enclosed current becomes I minus 2 pi C integral of R to negative 2 dr. The integral limits are A and R. After taking the integral, we obtain I plus 2 pi C times 1 over R with the limits A and R. So we can write I plus 2 pi C times 1 over R minus 1 over A out of the screen. Note that for the outer surface R equals B, then I enclosed is I plus 2 pi C times 1 over B minus 1 over A, which is out of the screen. Finally, for R greater than B, the enclosed current is the same as the surface case, that is, I enclosed equals I plus 2 pi C times 1 over B minus 1 over A, which is out of the screen. Now, with the numerical values, the enclosed current is obtained as negative 1.0022 amperes, which is out of the screen. The negativity in the result tells us that the direction out of the screen should be changed to direction into the screen. B. Find the direction and magnitude of the magnetic fields at points R equals 2 mm, 4 mm, and 6 mm. In this example, the current is distributed cylindrically symmetric. Therefore, we use the Ampere's law for the magnetic field. B equals mu0 times I enclosed over 2 pi R. For R is less than A, that is inside the shell, enclosed current is I, which is out of the screen. Therefore, B equals mu0 times I over 2 pi R. At R equals 2 millimeters, which is 0.002 meters, which is less than A equals 0.003 meters, we can use the formula B equals mu0 I over 2 pi R for the magnetic field. Then, with the numerical values, we obtain the magnetic field as 1 times 10 to negative 4 Tesla or 100 microtesla. And since the current is out of the screen, the direction of the magnetic field is counterclockwise by the right-hand rule. At r equals 4 mm, which is 0.004 meters in SI units, is greater than A and less than B, the enclosed current is I plus 2 pi C times 1 over R minus 1 over A, which is out of the screen. Therefore, the magnetic field is the following. Now we can substitute the numerical values into this formula. Therefore, we obtain approximately negative 1.38 times 10 to negative 4 Tesla, or negative 110.38 microtesla. Because the counterclockwise direction is positive, then the negative sign in the magnetic field tells us that the direction of the magnetic field is clockwise. Finally, at r equals 0.006 meters, which is greater than B equals 0.005 meters, the enclosed current is 1.0022 amperes, which is into the screen. Then with the numerical values, the magnetic field is obtained approximately as 3.34 times 10 to negative 5 Tesla, or approximately 33.4 microtesla. And since the current is into the screen, then the magnetic field is clockwise by the right-hand rule. To sum up, we draw all the magnetic fields at points r equals 2, 4 and 6 millimeters. Okay, that's all. Thank you for your attention. See you on the next video.